Hey everyone, and welcome back for yet another video. This one's probably going to be on the longer side, so get ready to hear my heinous voice for potentially up to 20 minutes. Again, just want to kind of address the comment that I received maybe once or twice in the last video, calling me a hypocrite. I am a hypocrite, but I'm going to slowly aim to undo your opinion of me after I start posting more complex videos. I just don't really think it would be right for me to start going into really advanced algorithms without covering the basic stuff first. So yeah, like I said, I'm a hypocrite, whatever. Today we're going to be covering sorting algorithms, which is particularly useful for me because my life is out of order at the moment and I need some tools to figure my shit out. And yeah, let's just go ahead and get into it. Like I mentioned, there's going to be a lot of content to cover here and I don't want to waste anyone's time. Alright, so let's go ahead and talk about sorting. So the first thing that we're going to quickly do is talk about a background. What are we doing with sorting? I imagine that most of you know it by now, but the general premise is that we have some list of items which are going to be out of an order and we want to be able to put them into an order. For the purposes of this video, I'm going to assume that those items are numbers and we want to be putting them in ascending order. However, it is the case that they could be things like strings, objects, whatever, and we may want to be putting them in a descending order or an ascending order. The point is you could use some sort of custom comparator function, but for now let's abstract that all away and just imagine that we're dealing with numbers that we want to be putting in ascending order. So there are a few considerations when we're talking about sorting algorithms that we want to be thinking about, and they are good to keep in mind because this is how these algorithms differ from one another. So the first thing to think about is how fast are we actually executing this sort? What's the time complexity of that in terms of asymptotic bounds? What about the space complexity? Is this an in-place sorting algorithm, meaning that it's going to be O of 1, or are we going to need to add some sort of auxiliary data structures in order to kind of work everything out? And then finally, is the sorting stable? What stable sorting basically means is that if we have a bunch of duplicate elements in our array, is the original relative order of those duplicate elements going to be preserved? So for example, if I have the elements in an array 3, 1, and then 3, is it going to be the case that in the final sorted array, that first 3 is still going to be coming before the second 3, or is it possible that their order may have switched? So moving on from there, let's just go ahead and say the following. I know there are plenty of sorting algorithms, and this is pretty much a very small percentage of them, but let's just say that these are some of the most popular ones. I've kind of deliberately left out bubble sort, but it's not too different from selection and insertion sort. And more or less the general premise is we're going to go through these 4, each of which kind of have their own unique way of solving this problem. And then we're going to look at the pseudocode for them, as well as the actual time and space complexity, and additionally whether they're stable. So let's go ahead and start out by getting into selection sort. So the general premise of selection sort is this. Basically, we're going to split our array into kind of 2 portions, and this is going to be a common theme of these sorting algorithms. And the 2 portions are going to be, we have an unsorted portion and a sorted portion. So basically the premise is this. We take the minimum element from the unsorted portion of the array and we move it to the end of the sorted portion of the array. And we just keep doing this until our entire list is sorted. So the way we're going to start out is that our unsorted portion of the array is the entire array and the sorted portion of the array has no elements in it. So the first thing we're going to do is iterate through the array, find the minimum element. So in this case, that's going to be the element 1, and we're going to move that to the front. See, now the yellow portion of the array is going to be what we delineate as the sorted part. So we're not going to touch that from here, we're simply going to append to it. And we're going to swap 1 with 3, which was basically the next element of the unsorted part. So similarly, now we're looking at element 8, and we know that we're going to swap element 8 with whatever the minimum element is in the unsorted portion of the array. Looping through, we can go ahead and see that that's clearly going to be the element 2. So we're going to take element 2, and we're going to swap it with 8. And then just to demonstrate one more iteration of this, now we can see that in the remaining white elements, the minimum is going to be 3. So we're going to take element 3 and swap it with 4. So now we can see that we're starting to kind of build up our sorted portion of the array, which is yellow. And as we continue to do this, we're going to go ahead and eventually generate a completely sorted array. So even though I've kind of gone through this and explained how it would work, let's go ahead and show off the pseudocode. And then by looking at that, we can actually look into things like the time complexity. Okay, so we have our selection sort method, and even though it kind of looks like Python, there are things that I've done that aren't actually Python syntax. So basically we're going to have a single outer for loop, which is basically looping through all of the elements of the list, and that's kind of going to delineate what our unsorted and sorted part of the arrays are. That I element is going to kind of be the thing splitting the two of them. And then every single time that we have I, we have a second loop where we have an element j, and then all j is going to represent is we use that second loop of j to go ahead and find the minimum element in the unsorted part of the array, and once we find it, we can go ahead and swap it with element I, thus making it so that we can build up that sorted portion of the array. So if you're relatively familiar with time complexity, you can see that this is going to be an n-squared algorithm because we have these two nested loops, and basically they're going to be pretty simple in terms of I is going all the way through the body of the array, and then j is just kind of stacking on top of I. So that's pretty textbook n-squared right there. In terms of space complexity, this is all in place. We're only doing swapping and we're never actually creating another array, so it's pretty clear that this should be O of 1 in terms of the amount of space that we're using. And then finally, in terms of whether this is a stable sort or not, recall that, like I said before, stable sort is when duplicate elements retain their original ordering relative to one another. We can clearly see that it's not, and I'll provide a counterexample. So let's imagine that we have the array 2, 2, 1. And so I've basically said the first 2 is going to be 2a, the second 2 is 2b, and then the third element is going to be 1. After that first iteration of selection sort, 1 is going to be switched with 2a. So then we're going to have 1, 2b, 2a. And then in the subsequent iterations of selection sort, things are going to be kept the same as before. So our eventual result is going to be 1, 2b, 2a, and clearly this is not stable. 2a and 2b have been flipped in the eventual ordering. Okay. Moving on, we have insertion sort. Insertion sort is definitely pretty similar to selection sort, but the main difference is that basically, as opposed to kind of appending to the sorted section at the end and finding the minimum in the unsorted section, what we actually do is just take the next element in the unsorted section and put it into the right place of the unsorted section. So the way that we start things out is we basically say, okay, the first element is the original sorted section, and everything else is kind of in the unsorted section. So as you can see here, we're using the same array as before, and we're going to try and sort it. So again, we have 3, 8, 4, 12, 1, and 2, and 3 is in the sorted section. So the next element to consider is actually going to be 8. So we look at 8, we say, all right, well, where in the sorted section is 8 going to go? Well, the sorted section right now is comprised of just 3. So when we actually go ahead and put 8 in it, it can just go right after 3. So now we have a sorted section of 3 and 8. Similarly, the next iteration of this is going to consider the element 4. However, the one difference here is that 4 is actually less than 8, but it's still greater than 3. So basically what we're going to do is swap 4 and 8. If it were the case that 4 was even less than the element in the position of 3, then we would have to do an additional swap there in order to eventually put 4 in the right place. So you can see here that we're kind of building up a similar thing to selection sort, where every single iteration of the loop, we can potentially do an entire other full sweep through that array to have to take our first element in the unsorted section and put it in the right place of the sorted section. So naturally, it means that we're gradually moving ourselves toward an n-squared algorithm. So actually looking at the pseudocode, again, it's pretty simple, but basically the premise is this. We have one basically index of a loop called end sorted, which is going to delineate the end of where the sorted section is. And again, that's going to start at 1 this time because we're basically initializing the first element as the first part of the sorted section. Then all we're going to go ahead and do is take the first list of the unsorted section, which is going to be called cur, and we're getting the index of that current element as well. And then all we're going to do is basically say, okay, while cur is basically less than the element behind it, we can keep swapping that through. And that way we're basically iterating through the sorted section and continuing to swap until that element is inserted into the right place. So as you can see, that's clearly n-squared because we're basically doing an outer loop, and then for every single iteration of the outer loop, we're doing an array insertion, which, as we covered in our last video, is O of n. In terms of the space complexity, again, this is going to be constant simply because we're not allocating any new arrays or anything along those lines. And additionally, we can actually go ahead and say that this is a stable sort because of the nature of how we're inserting our element. We're basically just going backwards through the sorted section and going until we find an element that is less than or equal to our current element that we're swapping through. So for example, if we were to actually find a duplicate, we wouldn't swap past that, and as a result, the relative order of those two elements would be maintained. Okay, next up we have merge sort. So merge sort's a pretty cool algorithm in the sense that it's actually implemented recursively. So basically what we do with merge sort is we have our original array, and all we're going to do is keep splitting it into smaller arrays. We're going to sort those smaller arrays, and then we're going to merge those two sorted smaller arrays back together so that then we can get our original array back. So let's go ahead and look at the process of how this might be done. As you can see, we're starting with an array of size 4 where the elements are 7, 2, 5, and 3. Like I mentioned, the first thing we're going to do is split this into two smaller arrays. So now we have two mini arrays of 7, 2 and 5, 3. From there, basically, we're going to take each of those arrays of size 2 and split them into two elements. So you can see we have 7, 2 here, and then subsequently we also have 5, 3. So now we just have 4 arrays of one element each. We've effectively reached our base case now of the recursion, where any array with one element is inherently going to be sorted. So what do we do from there? This is where we actually start merging them back together. So we know that 7 and 2, once merged together, if we want them sorted, should result in 2, 7. And similarly with 5 and 3, since those are out of order and we want to merge those back together, we should have 3 and 5. The final piece of the puzzle is taking these two arrays, each of length 2, and merging them together into an array of length 4. The way we do this is basically by having pointers at the indexes of both arrays, starting at the 0th index, and then continuing to basically take the element of the array that is smaller, where the pointer is lining up. So basically we have two pointers, one starting at element 2, the other is starting at the element 3, and we say 2 is smaller than 3, then the pointer moves up to 7, and then we would say 3 is smaller than 7, so now the pointer for array 2 is moving to 5, and then we would say 5 is smaller than 7, so now the pointer is moved up again such that it's out of the length of the array, and then finally, basically since the only element left to add back in is 7, we would go ahead and do that, resulting in a 2, 3, 5, and 7. So I know that was kind of abstract in terms of how we actually go ahead and kind of do that merging, which is why, of course, I have the pseudocode on the next slide. So merge sort is going to again be a recursive function, and all it's going to do is do the following. It's going to first check for a base case of when the list to sort is length 0 or 1, and if that's the case, it's considered sorted, we can just return it. Otherwise, we're basically going to get two lists where we take the left half of our original list and the right half of our original list, and we call merge sort on both of them, which should in turn return us a sorted array. So now we know that we have a left sorted array and a right sorted array, and finally we're calling our helper function merge to actually merge them together. Okay, so let's actually go ahead and now look at that pseudocode for merge. Basically, we know that we're going to have a pointer for list 1, we're going to have a pointer for list 2, and then we're also going to allocate a new array where we're going to store the actual result of the merging. So basically, we're looking at the pointers and the elements corresponding to the pointers for list 1 and list 2, and we're going to append the minimum element to our resulting array. And then finally, basically, whichever pointer was representing that minimum element, we're going to increment it. Eventually, the reason we have those two while loops below there is because we know that one of those pointers is going to reach the end of its given array first, and from then on, we want to be able to append all the remaining elements of the other array. Finally, we can actually return that resulting array. So what is the time and space complexity of all this, and additionally, is it stable? Well, basically we know the time complexity is actually going to be n log n, which is better than the n squared that we've seen in the past. The reason this is n log n is because basically by doing this splitting lists into two parts, we're kind of going into that essentially logarithmic time complexity of doing all of these binary splits, where at the same time the merging of them back together is inherently a linear time operation, and so as a result we basically multiply the two of those. Additionally, as far as the space complexity goes, we've mentioned that we're actually creating a secondary array called res in our merge function, and that is going to mean that ultimately this entire thing is going to be linear in terms of the space that it requires. Finally, this is actually a stable sort. It kind of depends how you actually implement the merge function, but assuming that you do it in a way where duplicates basically are always going to be chosen from the same array, and you kind of give one array priority over the other, then it is going to be stable. Okay, our final algorithm is actually going to be quicksort. So basically the premise of quicksort is, again, this is going to be recursive, and basically the first thing that you're going to do is go through your array and you're going to pick a pivot element. So your pivot element can be chosen consistently in many different ways. You could try and choose a median, you could choose the first element of the array, you could choose the last element of the array. But generally the point is, once you choose your pivot element, all you want to do is take all the rest of the elements in the array and basically move them such that all of the elements less than the pivot are going to be in a position before it in the array, and then finally all of the elements greater or potentially greater than or equal to the pivot are going to be a greater spot in the array. So let's go ahead and actually illustrate that so that you guys can understand what I'm talking about. So you can see we have a 5-element array here, and I've chosen the last element as the pivot, where the pivot is 3. So now, after basically doing this whole partition operation, we can see that we basically keep the relative order of all the elements, but it's important that all of the elements that are actually less than that pivot are to the left of it, and the greater ones are to the right. So you can see that 3 is in the middle, with 4 and 5 to the right of it, and 2 and 1 to the left. Then the recursive aspect of this is taking the parts both to the left and the right of the pivot, and also running quicksort on those. So now we're going to actually go ahead and demonstrate the pseudocode for doing something like this, so that you guys will know how to implement it in your own coding problems or anything along those lines. So let's start with the outer level recursive function, and then we can go into this helper function partition after the fact. Basically, we know that we have our array being passed in, and then we have a lower index and a higher index, where the lower index and the higher index basically delineate the parts of the array that we're currently trying to sort. So the first time that we call quicksort, the low and the high are going to be 0 and the length of the list -1. So basically the first thing we're going to do is get this PI, which is a partition index, and it's basically going to tell us where our partition element ended up in that array. So in the previous example, PI would be index 2 because element 3 ended up on index 2. Then from there, all we're going to do is go ahead and run quicksort on both the left side of the partition index and the right side of the partition index, which is pretty simple. So the more complicated part is actually doing the partitioning itself. So again, we're getting passed in basically the same parameters as before, which is the array itself and also kind of the current indexes of the elements that we want to actually go ahead and sort. So right now, the first thing we're going to do is actually find our pivot point, which, like I mentioned, we're using basically the last index of the array, hence we're getting the array at the high index. Additionally, we have this second variable called less than pivot, where this is basically going to be the point that you're swapping any element that's less than the pivot to. This is going to basically increase over time as we swap more elements into there, but we'll show that in a second in this for loop. So now we're basically going to look at all the elements from that low to high index, and we can call those j. We're basically now going to say if this element at index j is less than our pivot point, we can go ahead and swap it to the less than pivot position, and then we can go ahead and increment our less than pivot position by 1. The final aspect of things to actually do is make sure that the pivot point is at that less than pivot position. But yeah, the general premise is get everything to the left of it looking good, get everything to the right of it looking good, return the pivot point, recursively go ahead and quicksort both the left and the right of the pivot. In terms of the actual complexities of quicksort, so basically in the average case, this is going to be n log n. Why? Because generally the pivot that you should be selecting should hopefully partition our array into basically 2 relatively even sizes, where, you know, if we get lucky and the pivot that we choose happens to be like around the median, we know that the left and the right side of the pivot are going to be relatively even sized, and thusly it's going to be quicker to sort. So in the average case, this is going to be an O of n log n algorithm, which is really great. However, there is a worst case where this is n squared. If it's the case that the array is already sorted, what's going to happen is every single time that we choose the last element as our pivot, there's going to basically be nothing to the right of the pivot, and there's going to be everything to the left of the pivot. And then we're going to do the same exact thing, choose the last element again, and now there's going to be all the elements to the left of the pivot and nothing to the right of the pivot. And so we're going to end up doing n squared operations to basically confirm that, and it's going to save us no time. So that is something to consider with quicksort. Additionally, this is all in place. Again, we're not allocating any new arrays here, so the space complexity is constant, meaning it's O of 1. And then finally, to note, this is not a stable sort. It is the case that you may pick a pivot, which is a duplicate element, and as a result of picking that pivot, we may end up kind of messing up the order of elements that we originally had. So quicksort is not stable, but it is generally a pretty good algorithm, especially if you want to be optimizing on the space being used. Okay, so in conclusion, there were a lot of things to cover here, but hopefully this should be relatively familiar to at least most of you, unless you're pretty much a very recent programmer. These are all things that you do have to know. However, for the most part, at least in coding competitions, lead code questions, interviews, unless they very specifically ask you to implement one of these sorts as well, generally speaking, you are using built-in kind of language sorts, and those are going to be pretty efficient. Typically, those are n-log-n algorithms. So there are also other algorithms that we didn't cover. Like I mentioned, we didn't cover things like bubble sort, and additionally, there's an entire class of algorithms known as non-comparative sorting algorithms, where you're not actually directly comparing the elements with one another, but you're doing something else, maybe using some sort of hashing in order to kind of place them in different buckets, and then ultimately try and sort them from there based on which bucket they're in. So that's a topic for another video, but it is worth noting that there are kind of certain clever ways of sorting that can be very efficient in certain scenarios. Ultimately, guys, let me know if this video was useful. The last one performed nicely, so I guess being a hypocrite and selling out does kind of pay. But yeah, again, I hope this was useful. I didn't really go into why it is that you can't necessarily achieve better than O of n log n with comparative sorting algorithms, and truthfully I'm not sure that I will, just because I feel like if we start proving everything on this channel, then we're really going to take a while to get into kind of the more interesting content. But yeah, ultimately, again, I hope you enjoyed it, and